This set of notes is about LeChatelier's principle. So thus far we have learned what reversible reactions are, what the equilibrium condition is, how to calculate the equilibrium constant, and evaluate it using calculations. So this brings us on to the next piece of reversible reactions, and that's LeChatelier's principle. So LeChatelier was a French chemist, and he eventually came up with this principle after doing a bunch of experimentation that says if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Okay, so basically the idea here is that something that's at equilibrium always wants to return to equilibrium. And so if there's a stress or a change in it, the system will respond in a way that brings it back to the equilibrium position, back to an equilibrium position. So when we think about this, we think about stress, shift, effect. Okay, so what's the stress, what's the shift to relieve it, and what's the effect in the end? Okay, an analogy that we can use for this, I like this water tank analogy here. So imagine that I have two water tanks connected by a little tube down here on the bottom. And you would know that if you filled them up with water, they would fill up to the exact same level, both of them. All right, we would say they are in equilibrium, okay, with each other. So then if I were to go ahead and I were going to add water to the tank here on the left. Okay, so if I add that water, here's the stress that I've created. Okay, so the stress that I've created is to increase the water here. Okay, so LeChatelier's principle would say the system is going to respond in a way that relieves that stress, or in other words, brings that back down. And if that's the case, how does that do that? Well, it's got to shift water over here to the right. Okay, so the stress is to increase the water in the left. The shift is to send water over to the right, and then at the end what you end up with is you're back at the equilibrium position, but in this case the equilibrium position is a little bit higher than it was before, but still in a situation where both sides are at an equal high. Okay, same kind of thing happens in a chemical reaction. When we change the temperature, pressure, or concentration of one of the components in the system, the entire system will shift to relieve that stress and bring the system back into equilibrium. The end equilibrium position might look different than the beginning of the equilibrium position, but it will still be in equilibrium. All right. So again, the types of stressors that do this: one, change in the reactant or product amount or concentration, okay, change in the pressure in a system, change in the temperature in a system, and we'll also talk a little bit about catalysts to a system. So those are the types of stressors we think about when we think about LeChatelier's principle. Okay. To examine the effect of each of these types of stresses, we're going to use this reaction here. So ammonium plus water or plus oxygen goes to nitrogen monoxide and water. Okay, so, and with the coefficients that we have here. And this is an exothermic reaction with a delta H of negative 904.4 kilojoules per mole. Okay, so this is the system we're going to be using and thinking about how will this system change if we change the concentration of the reactants or products, change the pressure in the system, or change the temperature, or add a catalyst. So we're going to go ahead and we're going to start out with a change in the reactant or product amount or concentration. Okay, so the question we have here is, how does adding or removing reactants or products affects the concentration of the other reaction species? Okay, and the response to that is the concentrations change because the reaction is going to shift away from addition. Okay, so if I add NH3, so let's say I increase the amount of NH3 that I have. Okay, our shift is going to be to move away from that addition. So our addition was on the reactant side, so our shift is going to be toward the product side. Okay, or in other words, moving toward the product. Equilibrium shifts to the product side. So if that's the case, what's the overall effect of this? Well, the effect of it is that we're going to end up with more NO and more H2O. Okay, so that's the effect. Likewise, if we think about the reverse of that, if we remove NH3, so move NH3, again, the shift is going to be away from addition or toward removal, right? So we remove some NH3. So what's the shift going to be in this particular case? The shift is going to be to the right, right? We've lowered the NH3, so we're going to shift to the left, okay? Got my rights and lefts mixed up there. Okay, so by removing NH3, the reaction is going to shift to the left to replace that NH3, so we're going to end up with more reactants being made. The second kind of stress that we see is a change in temperature. Okay, so how does heating or cooling affect the concentrations of other reaction species? All right, so one way we can deal with this is we can go ahead and write the energy rate into the equation. So we know that from being negative 904, that means that this thing is exothermic, which means we're going to be getting heat out of it. Okay, so we could go ahead then and just write the kilojoules right into the product side. And if we write it into the product side, then we think the same thing that's going to happen, right? So heating is going to shift away from energy. Cooling is going to shift toward energy, okay, right? Heating is going to make it so we try to eliminate some of the energy that's produced. Cooling is going to get us to try to create more energy to replace the lost heat to an outside system. So heating shifts us away from energy. Cooling shifts us toward energy. So what's the stress? The stress that we're going to look at is heating here, okay? So since we've heated it, that means we've increased the energy. So I find where the energy is. Heating increases the energy. So what's going to shift going to be? It's going to be away from that heat, okay, in order to get rid of the heat. So the end result is that we are going to shift to the left, and thus the effect of this is we're going to make more reactants because our reaction is moving in the reverse direction. Likewise, if something is cooling, that means we're taking away heat. So what is the system going to want to do? It's going to want to replace that heat. How does it do that? By shifting to the right. And if we shift to the right, that means we get more products formed. Okay, so again, easiest way for me to think of this is just to go ahead and write the energy into the equation as if it is a reactant or a product. And then we can just deal with it, right? Heating is an increase in energy, cooling is a decrease in energy, and then we can treat it just like it's a reactant or a product. All right. The change in temperature value here has just a couple more caveats that go away from it. So you'll notice that if we change the temperature, that's also going to change the equilibrium constant K, right? If we go ahead and we increase the temperature, if it's exothermic, a shift to the left is going to increase the reactant concentrations, and it's going to decrease the product concentrations, okay? Thus, if we have K equals product over reactants, and the reactants are going down and the products are going down and the reactants are going up, what happens to K overall? K gets smaller. Okay, so in exothermic reactions, in an exothermic reaction, adding heat is going to go ahead and make K, or the equilibrium constant, lower. If something is endothermic, then, of course, we are going to go ahead and we're going to lower the temperature, and that's going to cause a shift to the right to replace that heat. Well, if we shift to the right to replace that heat, the amount of product is going to go up, and then the amount of reactant is going to go down. So likewise, K is product over reactant, product going up, reactant going down. Overall, K is going to increase for an endothermic reaction. So temperature is the only one of the stresses when we talk about LeChatelier's principle that has this effect on K, that can actually change K. So if we change the concentrations, that doesn't change the equilibrium constant. If we change the pressure, that doesn't change the equilibrium concentration. If we change the temperature, yes, it absolutely changes the equilibrium constant. The third kind of stress that we have is a change in pressure. So the question is, how does increasing or decreasing pressure affect the concentrations of other reaction species? So there are three ways in a chemical system to change pressure. The very first one is to go ahead and add or remove products that are in a closed system. So imagine that I have all of these gases in a closed system, and I go ahead and I increase the amount of NO in it, or the amount of H2O in it, or the amount of O2 in it, or the amount of NH3 in it. All of those, if I added new particles of that, would be the exact same as changing the concentration or changing the overall pressure in there. And so as a result of that, more particles equals more pressure, less particles is less pressure, but I treat it just like an increase or decrease in concentration. So increasing the number of H2O particles would do what? It would go ahead and it would shift the reaction to the left, etc. Okay? Another way of changing pressure is to add some other non-reactive gas into the system. So let's say into here, I go ahead and I put nitrogen gas. Okay? Well, nitrogen gas is going to have more particles in the system and create more pressure. However, the new gas is not involved in the equilibrium, so there's no effect on the equilibrium in this situation at all. The equilibrium position stays the same, the equilibrium constant stays the same, the partial pressures stay the same, etc. Okay, so there's no effect. The third way is the one that we most often think about, which is changing the volume. So if I decrease the volume, there's more pressure. If I increase the volume, there is less pressure. We know that from our gas laws. Okay. The equilibrium in this particular case is going to shift based on the number of gas particles. What do I mean by that? If we change the pressure by changing the volume, then what happens here is as the pressure goes up, you're going to shift toward fewer stoichiometric moles of gas, which lowers the pressure, right? So if the pressure goes up and I can make a reaction go such that we create fewer gas particles, that's going to bring the pressure back down. If the pressure goes down, I shift towards more moles of gas. We raise the pressure. All right, so taking a look at our system up here, let's say we increase the pressure. Okay, so our stress here is that the pressure is going up. Let me count my moles of gas on both sides. So this is 4 plus 5, which equals 9 moles. Over here, it's 4 plus 6, which equals 10 moles. Okay, so if I'm going to go ahead and increase the pressure, we want this reaction to shift in a way to lower that pressure down. How do we do that? By shifting towards fewer stoichiometric moles. So we're going to shift from 10 toward 9. So our shift is going to be to the left. All right, so the shift is to the left when we increase the pressure. And what's the effect of that? Well, the net effect of that is then we're making more reactants. Okay, so more reactants get produced. The second thing that happens here, if we decrease the pressure, so again, 9 moles, 10 moles, pressure is going down. What happens? Well, the system is going to want to restore that pressure. So it's going to do that by creating more gas particles. So it's to the right, and being more products are getting produced. The last stress that we have is adding catalysts, okay? So if we think about how does a catalyst affect the concentration of each species, it doesn't in the process. But what it does is it increases the forward reaction or rate of reaction and the reverse rate of reaction. It does both. So as a result of that, you don't actually get a shift left or right, but what happens is that equilibrium is reestablished more quickly. So again, catalysts do not affect the equilibrium position. They just reestablish the equilibrium much more quickly. On the last set of your notes, you do have this very lovely diagram from Compound Interest, which is one of my favorite chemistry graphic sites. And this just basically, once again, defines for us what we mean by equilibrium. Defines LeChatelier's principle and then tells you about what does concentration, temperature, and pressure do to the equilibrium as we go there. And then gives you a little clue about here, down here about a catalyst as well. So again, sort of everything we've done today summarized into one lovely graphic. That's everything you need to know about LeChatelier's principle for notes for right now.